This is a recast of the 4,600-word piece, Feedforward Neural Networks, FNNs, from Chinapat AI. This article explains the advantages, disadvantages, and applications of feedforward neural networks, FNNs, in machine learning and AI. Let's listen in.
Artificial intelligence has gone through a major transformation in recent years. One of the key tools in this new era of AI is feedforward neural networks, or FNNs.
That's right. FNNs are a type of neural network architecture that passes information in one direction. They are composed of input layers, hidden layers, and output layers. Each layer contains artificial neurons, which take input and produce new outputs.
FNNs have great importance in the field of machine learning due to their ability to classify data accurately and efficiently. They can process a large amount of data and identify complex patterns that might be tough for humans to recognize. Plus, they can learn from past examples and adapt to new data.
Exactly, which makes them perfect for creating sophisticated models used in industries such as finance, healthcare, and marketing. As such, understanding FNNs is essential for students, researchers, and professionals in the field of neural networks.
But what are the advantages and disadvantages of FNNs?
One key advantage is that FNNs are able to avoid overfitting. This is when a model becomes too complex, and instead of learning generalizations, it starts memorizing examples. To prevent this from happening, FNNs use regularization techniques such as dropout and weight decay. Other benefits of using FNNs include their activation functions, which aid in smoothing out values and converting them to probabilities, and their structure, which is composed of multiple layers that extract relevant features to improve the accuracy of the network's prediction.
Although there are many advantages to using FNNs, there are some disadvantages to be aware of as well. For example, they require large datasets and a lot of computation power to train, and they can be difficult to debug due to their complexity.
That's true. Additionally, FNNs are not always the best option for problems that require temporal processing, such as predicting time series data or understanding natural language. In these cases, recurrent neural networks might be more suitable.
It's clear then that FNNs have their uses and drawbacks, but overall they offer many benefits when it comes to machine learning. Now let's talk about their applications in various fields.
Absolutely. FNNs can be applied in a wide range of tasks, including image and speech recognition, natural language processing, and predictive algorithm development. They are also used for financial forecasting and engineering applications.
That's right. FNNs generally have an input layer, one or more hidden layers, and an output layer. The input layer accepts data and passes it to the hidden layer for processing. The hidden layers perform complex computations and generate output that gets passed to the output layer for final output.
Right, and the number of layers and the number of neurons within each layer influence the accuracy of the network's output. Also, activation functions in FNNs play a key role in introducing nonlinearity into the neural network.
Yes, a commonly used activation function is the rectified linear unit, ReLU, which is a simple nonlinear function that takes the maximum of 0 and its input. Another commonly used activation function is the sigmoid function, which maps any input to a value between 0 and 1.
And then there's the backpropagation algorithm, which is a widely used method for training feedforward neural networks. It involves propagating the errors produced by the network's output layer back through the network to adjust the weights and biases. Do you think this process can be computationally expensive?
Yes, it definitely can be computationally expensive, and it may even get stuck in local minima. Therefore, various modifications have been proposed to improve its efficiency and effectiveness.
Got it. So in conclusion, FNNs are an incredibly powerful and versatile tool in machine learning and artificial intelligence, making them particularly useful in fields such as finance, healthcare, and climate science.
That's right. So let's dive a little deeper into some of the specific benefits of FNNs. First and foremost, one of the most significant advantages of using FNNs is their ability to eliminate human error.
Absolutely. With FNNs, we have an excellent tool to automate tedious tasks, reducing the workload and making sure that the data is free of human-induced errors. This, in turn, enhances the accuracy and reliability of results, which is critical in fields such as medicine, finance, or security, where even a minor mistake can have severe consequences.
Right. Additionally, FNNs can provide faster decision-making processes than conventional methods due to their parallel computation capabilities. The FNN architecture enables simultaneous processing of multiple inputs, leading to a decrease in computation time compared to traditional techniques.
Also, FNNs can be used for a variety of tasks such as classification, regression, and prediction. They have the ability to learn from historical data to make predictions about future outcomes, which can save time and money by minimizing the need for human analysis and allowing for faster decision-making.
And FNNs can accurately analyze large amounts of data and identify complex patterns to improve financial decision-making. For example, in a study conducted on skin cancer diagnosis, the FNNs were able to classify malignant, benign, and normal skin images with high accuracy.
Exactly. So as we can see, FNNs have a wide range of applications across multiple industries that can benefit from their ability to quickly sort through large amounts of data and provide accurate results that are free from human error.
That's right. But as with any technology, there are limitations. One major limitation is the lack of ability to handle temporal data, which means that they are not suitable for many time series prediction tasks.
Additionally, FNNs are not well suited for dealing with missing data or noisy inputs, as they rely on complete and reliable input information. Finally, the training process of FNNs is quite time-consuming and requires a significant amount of labeled training data.
And on top of this, a major challenge in training FNNs is overfitting. Overfitting is when the model memorizes the training data to the extent that it fails to generalize to new, unseen samples.
To combat overfitting, several regularization techniques have been proposed, such as L1 and L2 regularization, early stopping, and dropout.
Another limitation is the lack of interpretability. FNNs are so complex that it can be difficult to understand the logic behind the model's decisions. This lack of transparency can be problematic in industries where transparency is necessary, such as healthcare or finance.
Exactly. In addition to this, FNNs require a significant time investment to train properly. Each iteration involves passing input data through the network, comparing the output to the desired output, and adjusting the weights of the connections between neurons accordingly.
Additionally, as the number of input and hidden layers increase, and the number of nodes in each layer grows, so does complexity. This complexity can lead to difficulties in training the network, as well as increased computational resources required for processing the data.
It's important for researchers to consider these challenges and explore alternative methods to address high complexity in larger tasks.
In addition to the major types of activation functions, there are several other variations that have been proposed for specific applications. For example, the rectified linear unit, ReLU, is very popular in recent years because it has been shown to outperform other activation functions in deep neural networks.
And finally, the future of FNNs looks bright and is expected to revolutionize many industries. However, their limitations must be addressed to fully realize their potential.
Right. FNNs have trouble dealing with dynamic input patterns, and they are highly susceptible to training bias. They can also be computationally expensive, and they require a large dataset for training.
To address these issues, researchers are exploring new techniques and strategies to enhance the performance of FNNs.
That's right. For example, the integration of FNNs with other machine learning algorithms has been found to produce more accurate and robust models. This is especially important for applications such as image recognition and speech processing.
And improved computational power has been a major contributing factor to the development of FNNs. With modern hardware technology, more complex neural network structures can be created with higher numbers of neurons and layers.
Absolutely. Improved computational power also enables faster training and more accurate predictions, which makes FNNs a practical solution for a wide range of applications.
The potential of deep learning in healthcare is immense. It can be used for early detection of diseases, personalized medicine, and even robotics and autonomous vehicles. The possibilities are truly exciting.
They certainly are. Deep learning is also being used extensively in finance, particularly in fraud detection and risk management.
Indeed. And as technology continues to develop, so will the potential of FNNs and deep learning in various industries.